We'll start now. We'll have a quick review on what we have discussed in the previous class. We were discussing about this linear regression. Quickly, we will recollect. So last class, what we discussed was regarding this Bayes technique, right? Bayes technique of linear regression model. So the recap is like this: the observation T is equal to W transpose phi of x plus epsilon. So that is the parametric model what we are having. Epsilon is the random variable, which is modeled as Gaussian, which means 0 and variance 1 by beta. And x, bold x is actually the vector, right, which is the input, and the observations are the scalar, right, like T, right? So this is what the problem is. We are interested in finding out what is that value of W. Estimate W is the problem formulation. Right, so to attack this problem, we are interested in estimating W. So we have to look for the prior density function associated with W. That is, f of W is going to be your prior density function. And then we have what is called this posterior density function, f of W given T. What is given here is the posterior. And f of T given W is going to be your likelihood function. And they are related using this Bayes relationship. F of T given W is f of, there is a correction here, right? So this is W given T. Is f of T given W into f of W divided by f of T. So this is the relationship between the posterior density function and likelihood function. And we look for maximizing this posterior density function, which is basically this map, right, which is equivalently maximizing what is there in the right hand side. Denominator f of T doesn't have W in it, so that is not playing role in maximizing that. Numerator, we have f of W also, prior density function is available, right? So we have two approach in solving this. One is, if we assume f of W is uniform distributed, that is constant. If you assume this f of W is constant, we have f of T given W likelihood function that allowed to be maximized. So in that case, f of W is assumed as constant, and that solution is what we call it as maximum likelihood solution, right? And the another way to attack this problem is f of W. F of W, what is given here, can be modeled as this prior, right? So this prior f of W can also be modeled as Gaussian. So if f of W is also, right, Gaussian distributed, multivariate Gaussian distributed function, right? F of W is assumed as multivariate Gaussian density function with mean vector m0 and covariance matrix S0. And the posterior density function f of W given T is a posterior density function that also follows Gaussian. If f of W is Gaussian, f of W given T is also the Gaussian, and it's a multivariate Gaussian density function, f of W given T. which is going to have this mean vector given as Mn and the covariance matrix given as Sn, as you see here. So once this is known, then your solution, the estimate W cap, right, is nothing but Mn that we discussed. These things we already discussed. I'm just recollecting what we discussed in the previous class, right? So your W cap, the estimate is Mn itself. That involves the covariance matrix of W, and then we have a covariance matrix. Sn is going to be your posterior density function covariance matrix, and they are related with what? The covariance matrix of this prior density function, and the basis function phi is there, and T is the observation vector, and mean vector is also available, M0. So this is the relationship. And in fact, we had a specific case when we choose this M0 as 0 and S0 as this identity matrix with the diagonal elements as 1 by alpha, right? Right. So this is a special case when we choose this S0 to be 1 by alpha I diagonal elements, or 1 by alpha of diagonal elements are going to be 0. So if we choose this M0 to be 0 and S0 to be like this, the whatever we had in the expression for this Mn, right? So that boils down a very simple expression, what you see here. We get the solution like Mn is equal to phi transpose phi plus alpha by beta I, the whole inverse phi transpose T. This is the final story, right? The final statement, what you have to understand is the estimate of this W is given by this, right? So this is looking like the least square setup solution with regularization, right? We had a discussion on least square solution with regularization, where we had a solution which is of exactly this form. In place of lambda, it is now getting replaced with alpha by beta. So what we have to understand from this Bayes approach is, Bayes technique is the solution of this Bayes technique is like a regularization. So other way around, regularization, when you do this regularization, right, in the linear regression model, you are indirectly doing actually the Bayes technique, because you are exploring the value of lambda, right? So indirectly you are exploring that value of this alpha and beta, right? In fact, this alpha as well as beta is not really known to us, right? Because 1 by alpha is the assumed variance of the unknown variable W, which we are trying to estimate, right? And beta is 1 by beta is related with the noise. That is also not known to us, right? But if that is known in some other mean, then we can actually use it, this expression, directly to find out the estimate for W, which is given by this Mn. But in general, this is like a solution of the regularization in which this lambda is exactly equal to alpha by beta. When lambda is alpha by beta, right, we say that regularization technique and the Bayes technique are one and the same, right? This is what actually we discussed in the previous class. Today what we are going to discuss is that kernel smoothing. We will start with this actually. Okay, what you now see on the slide is about the kernel smoothing. So what is that kernel smoothing, right? See, you know that y of x, right? So that is nothing but the model is W transpose phi of x. So that is the model. The linear regression model is like this, right? Now using this Bayes, you are going to replace this W with what? Mn. You are going to replace this W with Mn, what we had the expression which we discussed in the previous class, right? This Mn. So you have this y of x. Y of x is in place of W, it is replaced now here Mn transpose phi of x. And we got a relationship, this Mn in the previous slide, I mean Bayes technique, like beta phi of x, the whole transpose, Sn phi matrix, this is the matrix here, transpose T, right? So this expression is actually coming from the Bayes, right? So what we had it earlier. So the expression for this Mn, which we took from the Bayes technique, is actually represented here. So in place of W is now replaced with Mn, and the Bayes expression for this Mn is now being replaced here. And this can also be written. So this is like, you know, that phi transpose T, this part is the matrix times the vector here, which we can write it as the linear combinations of the columns of the matrix phi transpose. So equivalently, this matrix product can be represented in terms of the summation sigma n equal to 1 to n beta phi of x transpose Sn. In place of this phi transpose T, right, you have here phi of xn into Tn, where this phi of xn is basically the vector, right, and Tn is the scalar. What is done here is this matrix multiplication, right? So what we are really having here is Ax, right? Suppose that if the matrix A is having A1, A2, and so on up to this AN, the columns of the matrix, we can write it as a linear combination of the columns of this matrix A, right? So that is what exactly done here, right? So it is like, suppose my vector X is having that element of X1, X2, and so on up to this Xn. Then we are actually doing that linear combination of these columns of the matrix A, that is X1 into A1 vector plus X2 into the A2 vector, and so on. It goes like that, right? The linear combinations of the columns of this matrix A. So here phi transpose T, here in this phi transpose is a matrix and T is a vector here, and which is written as the linear combination of the columns of this matrix phi transpose, which is basically phi of xn, right? The columns of this matrix phi, if you recollect, it is going to be phi of x1, phi of x2, and so on. So you are having this linear combinations of these columns of this matrix, right? So this is a way how we are writing. But what is more interesting now is if I relook into this expression and if I replace this part, starts from here, this beta into phi of x transpose Sn phi of xn, right? So you are going to replace this one with what is called the kernel function. This is the kernel function. This is the kernel function here. So in the original expression, we had what is called the basis. This is a basis function. But now you are getting the linear regression model, which is given like this: y of x that is equal to sigma n equal to 1 to n. There are the training data, k of x comma xn into tn. Tn is a scalar and k of x comma xn is the kernel function. What I'm trying to say here is, instead of looking for the basis function, originally we were interested in finding out what is that basis function to be used in modeling this linear regression model, like Gaussian, polynomial, and so on. Now, instead of looking for the basis function, you are actually going for directly what is called the kernel function. The kernel functions, the value kernel function is the one which we must be able to decompose or represent this k of x comma xn as the product of this term, right? Phi of x transpose Sn phi of xn, right? So not in arbitrary function can be viewed as the kernel function. The kernel function, right, you must be able to decompose like phi of x transpose Sn phi of xn. There are many kernel functions actually available, right, for doing this linear regression model. Gaussian kernel function can also be used. Gaussian basis function is different. Phi of x can be modeled as Gaussian basis. That is different. Now what I'm telling here is the kernel function can also be modeled as Gaussian. In that case, we call it as a Gaussian kernel, right? We are having some list of kernel functions available, valid kernel functions to be used to do this particular task. And the list I will discuss that one in the next class. The slide I will show you later on, right? But what you have to understand now is, instead of the basis function, instead of this basis function, now it is getting replaced with the kernel function, right? So that is the thing. Instead of the basis function, you are now going to use this kernel function, and kernel function itself is going to have some tuning parameter, right? So that needs to be tuned. That is a task now, right? So the flow is like this. We got an expression for the Bayes solution for the estimate of W, which is given by Mn, and you are replacing that solution here in this expression for y of x, and a simple rearranging, right, in a matrix in the form of linear combinations of these columns of the matrix, you are able to represent as in the form of a kernel function. This is what we call it as kernel trick, and many places we are going to use in this course. In support vector machine, we are going to use this kernel trick, right? And even in dimensional reduction technique, we are going to use this kernel trick. This is in pattern recognition, machine learning, right? So this is what popularly called as kernel trick. Means we don't want actually this explicitly this basis function, right? So instead of having this basis function, because basis function can be viewed as mapping that vector to the higher dimension, right? So because you are having a vector x, and then you are actually creating phi naught of x, phi 1 of x, phi 2 of x, and so on. So that forms this basis function, right? So it is like phi naught of x, and then phi 1 of x, like that, right? So it is basically you need m basis function, which is quite large in general. In practical application, we use this one as very large, like hundreds, the very big basis set of basis functions we use, and the computation is actually becoming complicated, right? So now you are replacing those things with the kernel function, and the kernel function is very simple, and it is enough to tune the parameter of this kernel function to do this task, right? So this technique is what we call it as kernel smoothing of the linear regression, right? So what we are doing here is this subscript n. This subscript n is a training data, and you have the corresponding target, right? So you have observation x1 and the corresponding target as t1 observation, right? x2 and then t2. So these are all the training data what we are having, xn, and we have this tn. So these are all the training data available, right? So using this training data, you are smoothing, you are trying to find out what is the value of this y of x using this kernel function. One such kernel function, what you see here is like this, right? So this is basically, you can now for time being, you can understand this one with the scalar y of x instead of going for this vector. So in this, this x and this xn, what I am considering now is a scalar quantity and having some range, for example, ranging from 0 to 1. Let us assume that is like that. So this is 0 to 1. So let us say this is x here. And you have, this is, okay, let me put it as x1 and this is x2 here. And what you see, this color shade in this is the magnitude of this kernel function, k of x1 comma x2. It is like that. So you have a higher value in the diagonal, and the off diagonal elements are going to be very less, right? These values are there in this. This is the kernel function what you see here, right? So if you tap one particular row of this matrix, and if I plot it as a 1D plot, you are getting this peak. This peak corresponds to this region, right? And this peak corresponds to this region, and this peak corresponds to this region. So what you see in the left side is just 1D plot of whatever you see it in the right hand side in the image format. This is the typical kernel function, right? So in case of this, if you are given a kernel function, if I want to know what is that, let us assume that it is already tuned, right? This kernel function is ready, right? Suppose if I want to know about the value of y of x, and you are given the training set like x1, x2, say, let me choose only 3 here, x1, x2, x3, they are the training data, right? So let us say your training data are like this location. This is one training data, and we have another training data, which is x2 here, and somewhere here, this is x3 here, right? So, and for this x1, x2, x3, you have a corresponding observations. The corresponding observations are t1, and you have this t2, and you have this observation t3, right? So you have this 3, right? So now what you have to do is, for, let me put let us say this is x1, and somewhere here x2, and this is going to be your x3 here. So this one is x1, x2, and this is x3. They're all the training data now, right? So if I want to know what is that y of x, some arbitrary x, what I'm having, so somewhere, anywhere you can choose, right? So I mean, given the problem, right? So let me say this is going to be your x, right? So this is going to be your x. What you have to do is, you have to actually identify this value, this kernel function value. these three values, right? So let me put in a different, right? So this kernel functional value, right? And the corresponding, the target value, T1, T2, and this T3. You are doing this linear combination. The kernel functional value, what is marked in a circle form here, and the corresponding target T1, T2, T3. If I do this linear combination, you actually get this y of x. So now the task is actually finding out the kernel function and the tuning parameter available in the kernel function. This model is popular, right? So this is actually coming from the base, starting point is base, and then we had an expression for y of x, and we simplified the way how it is written in terms of this kernel function. The advantage of using this technique is we don't want more number of basis function. Instead, it is enough to have only the kernel function. Kernel function, instead of going for the basis function, we are actually looking for the proper basis function. Not only that, you have to actually tune the unknown parameter available in the kernel function, right? So that way only the problem boils down. So in this case, the problem is to tune unknown parameter available in the kernel function using the training data. Using the training data, you have to tuning in the sense that you are going to divide the data into three parts: training, testing, and then validation, right? And you have to do it for, tune the parameter such that it works good for the testing data. Once this is freezed, then it is launched, right? After doing this proper validation, right? So it is like, you are going to have a training data in this expression. Whatever is given here, the subscript n, indicate that is a training data, right? You are using n training data here, right? And you are doing the linear combination of this corresponding kernel functional value into that corresponding target Tn to get the actual regression model y of x. This is what we call it as kernel smoothing technique. And this is the last technique as far as this course is considered regarding the linear regression model. Next class, we are actually going for this classification part. So as far as this linear regression model is considered, we started with the probabilistic model actually, right? So we had the maximum likelihood solution, Bayes technique, right? And the least square solution, least square with regularization. And then finally, we had the kernel smoothing. These are all the different ways how we do this linear regression. Still, we have other methods also, but that is out of scope as far as this course is considered. We will actually stop this linear regression model up to this kernel smoothing. And we know the relationship between all these techniques, right? One is maximum likelihood solution is same as that of the least square solution if the noise is Gaussian. That is an important property. And in case of maximum likelihood solution, the prior density function of the random vector W is assumed as constant. And in case of Bayes technique, f of W, the prior density function is modeled as multivariate Gaussian density function. And in case of kernel smoothing, we are completely replacing this basis function using this kernel function, right? And this technique is what we call it as kernel smoothing technique, right? So now once this model is known in linear regression model, whatever the technique you adopt, once this model is known, right? So we would like to see how this predictive distribution is going to be, right? So that with that, we are going to wind up for the regression part. Predictive distribution, what does it mean? This is important. This is more general about the linear regression model. Any technique you use it, right? Right? We have what is called the predictive distribution. Predictive distribution means for a given x, right? How the, you just see this expression alone. This is the predictive distribution density function, which is also going to be Gaussian. It is also going to be that Gaussian distributed with variance sigma n square, what is given here, that consisting of two terms. The first term is 1 by beta. 1 by beta relates with noise, as you know. The second term is phi of x transpose Sn phi of x. You know what is Sn, right? It is going to be that covariance matrix of the posterior density function, right? So in Bayes technique, we already discussed that, right? So now predictive distribution is basically for a new x. For the new x, how that density function of t is basically the noisy observation, right? For the new x, right, how the density function of the random variable t is distributed. So that actually gives you the predictive distribution, right? And this capital N indicate the number of data, training data being used. As the number of data used for modeling the regression is keep on increasing, then the variance of this predictive distribution is going to decrease. So this one you can understand with illustration. Once again, we'll go through that slide after showing this figure. This figure will give a little more clarity. Then we'll come back again to that same slide to understand what is the predictive distribution, right? So what is this figure indicate? This is basically the linear regression model for fitting the sine wave, right? What is given in this figure, this green is actually that original sine wave which you are trying to fit, right? And your training data is actually obtained from this only, right? So few samples from this green, what is given here, right? So that is what the thing. And you are going to have now only one observation, right? The noisy observation, what is given here in a blue circle. So in that case, once you have this observation here, right, then you are trying to find out what is that value of t for various range of x values, right? So remember that you are having only one observation. I mean, it's nothing but the training data is only one in that first subplot. Here the number of training data is 2, and here in the third subplot the number of training data is 4, and here we have more number of training data available, right? So what is given here, the shade, the pink shade, right, is actually the predictive distribution, right? Predictive distribution, with this red color as the mean of this predictive distribution. This red is the red color, right? What is marked here in the red is the mean of the predictive distribution. And for every values of x, you are actually having that guess for phi of x transpose m. Yes. So if you find out this mean, the mean of the predictive distribution, as the number of data are increasing, right? So you are getting this red follows, the sine wave like this, right? So what you see here is different fitting curve with only one data. What are the possible? See, as I told you, you are going to take that value of W and then you are going to fit the curve W transpose phi of X. That is the thing. You are getting the possible curves available in the subplot 1 with only one training data, and with 2 training data, the possible plots, and 4 training data, the possible plots. And if the number of training data is actually keep on increasing, the possible plots for this regression model is these things, So that all the things in the last subplot is almost following the sine wave, as you see here. More the data, you are getting that error due to only noise. So that is what I just wanted to show you this particular slide. What you see now here is this, the variance of this predictive distribution for every values of X. As I told you here, this is this plus sigma and minus sigma, above and below this mean, what you see here, right? That variance is going to be that function of every values of X here, right? And that is actually contributed by 2 terms. One is 1 by beta, which is due to noise, and the second term is actually the basis function and the covariance matrix of the posterior density function Sn, right? As the number of data keep on increasing, this variance is actually keep on decreasing. That is what this figure is showing. As you see here, this variance is actually keep on decreasing, right? The shade is actually decreasing, right? That means that the variance, the predicted distribution variance is actually keep on decreasing as the number of data are keep on increasing, as you see here, right? And as it is having 2 components, and if this number of data capital N is sufficiently large, the contribution to this variance is only due to this noise 1 by beta, which we cannot remove, right? So originally the variance of the predictive distribution, which is actually having 2 terms, one is 1 by beta, which is contributed by this noise, and then the second term that involves the covariance matrix of the posterior density function and the basis function, right? N keep on increasing, the number of data keep on variance of this predictive distribution, the contribution is mainly due to this first term, the noise, rather than the second term. Second term is almost going to end up with 0, and still we have that variance is so the predictors is get. So what understand the various technique in